We will look at the solutions to the posted sample midterm exam from fall 2016. This video will solve problem 1. So part A of problem 1 is on flex continuity. So we need to determine where the dot should be placed on the secondary for the given operating conditions. So when the switch is on, the current enters the dot on the primary side winding, and therefore when the switch is turned off, we need a current that continues to enter a dot on the secondary side. Looking at the secondary side, this diode here can support a current only such that it enters the top terminal of the secondary winding, and since we need a current to enter a dot, we would place the dot at the top so that when the switch is turned off, the diode supports a current that enters the dot at the top in the secondary winding. So the answer for this is dot at the top end of the secondary winding, and since you need to explain in just one sentence, I would write current needs to enter a dot, needs to enter a dot in secondary, and diode only supports current entering the top terminal. Okay, so putting these two together, we can determine that the dot should be at the top. So once that is determined, then the problem also requires us to calculate the output voltage VO, and for this we could use the volt-second balance, and we can do it for any winding, but we will do it for the primary here, for primary. Okay, so maybe you can just realize that this is a flyback transformer and use the derived input-output relationship. But if not, you can actually draw the waveform for say V primary and then write the volt-second balance explicitly. The duty ratio is 2/3 or 0.667. I'll just write as 2/3 and this be 1, and the x-axis T, T over Ts. Okay. Alright, so during the on interval, the voltage is 50 and it becomes negative. Okay, so that would be the V primary voltage, and on interval this voltage is 50 volts. And looking at the dots, dot polarity, when the switch is off, the diode conducts, and this voltage here defined with respect to the defined positive at the dot with respect to the dot at the end, if you call that as V secondary. During the off interval, V secondary equals V out the way we have defined it. So this voltage would be V out divided by N when referred to the primary side. Writing the volt-second balance equation, we have 50 times 2/3 plus VO over N times the duration is 1/3. Okay, and that is equal to 0. The 3's can be cancelled. So what we have is VO over N equals negative 2 times 50, 100. N is 0.2. Okay, so it's given here, it's 1:0.2, so N is 0.2. Therefore, VO is negative 100 times 0.2 or negative 20 volts. Part B of problem 1, we are given a converter that we have actually not studied. This is actually called as an active clamp forward converter. But it doesn't matter, we can actually solve this problem using the basic principles of isolated converters, mostly volt-second balance. So when the switch is on, the current enters the dot and flows through the switch here. And simultaneously this is a positive voltage. This diode is forward biased and acts like a buck or a forward converter. But what we are mostly interested in finding out this capacitor voltage VC is the primary side voltage, and so when the switch is turned off, we need a current to enter the dot, and there is no possibility of a current entering the dot on the secondary side. So the current would actually flow in this way through this switch, which is now turned on, into the capacitor, and then enters the dot, completing that path. Okay, so the winding voltage, the primary winding voltage, would be V in during the DTS period when the switch is on, and negative VC because we are applying the positively marked terminal here to the undotted end, and negative to the dotted end, and we are going to define V primary with this polarity. So let's draw the waveform of V primary here. Okay, so that's V primary, and I will again write it as T over Ts, the x-axis. The D is 0.4, so it says this is 0.4, and this is 1 complete switching period, it's 1. So during the on interval, the voltage is the V in, or 100 volts, and then it's negative. Okay. So this is 100 volts, and this voltage here would be the positive end is connected to the undotted end, therefore this will be called as minus VC. That's the primary voltage. So if we write the volt-second balance equation, we will write this as 100 times D of 0.4 minus VC times this duration here. Okay, that's 1 minus D, or 0.6 okay, times 0.6, 1 minus DTS. Okay. That is equal to 0, or VC, capacitor voltage, is 100 times 0.4 over 0.6, and that is 66.67 volts. So that is the first answer, VC. Okay, the second part requires you to calculate the output voltage, V out. Okay. So for that, it may help to draw the secondary voltage, which is exactly same as the primary voltage, except it is scaled by the turns ratio, which is given 1:0.2, or N equals 0.2. So I will go ahead and draw the secondary voltage waveform, V secondary. So that will be a positive during that 0.4 TS period, and a smaller magnitude negative for the remainder 0.6. This is 0.4, that would be 1 T over Ts. Okay, so this magnitude here is N times, so we are writing V secondary equals N times V primary. V primary is right here, therefore it will be 100 times 0.2, or 20 volts, and the voltage here would be minus 66.67 times 0.2. In fact, actually does not matter, but I will write that. What matters to determine the output voltage is the voltage which we normally define as V rect for the rectified voltage. So if I draw the waveform of V rectified, it will be same as V secondary whenever it is positive. So it's 20 volts here, and then it's 0 when the voltage is negative, because the diode prevents the V secondary being applied to this point when the V secondary is negative. So this waveform is V rect. Okay, then we know that because VL average is 0 in this part of the circuit, the V rect average is also same as the output voltage. Okay? So V rect average from the circuit is equal to V out, and from the figure here it is 20 volts for a duration of 0.4 Ts divided by Ts. That's it. So that would be 8 volts. Okay, that is the complete answer. Part C of problem 1 is related to the transformer design lecture. So you are given a transformer which is excited by a voltage source Vs, which is drawn here, and we need to determine the number of turns for both the primary winding and the secondary winding, given the turns ratio is 2 to 1, N primary to N secondary. So there are two ways of doing this. I would use the definition of voltage rating for a winding that we introduced in the lecture. So V rating, I'll call this as V primary rating. Okay, so by definition, rating is maximum positive volt seconds. Positive volt second. Okay, that is the product of voltage and the time divided by period. Okay. So if you apply that definition to the voltage here, the maximum positive voltage, the positive volt seconds is applied from 0 up to 5 microsecond, but it's not a constant voltage. So we'll write the maximum, we'll write the positive volt seconds as 100 volts for a duration of 2.5 microseconds plus 50 volts for a duration of another 2.5 to 5, which is another 2.5 microseconds duration. Okay, that's the positive volt seconds applied divided by the total period, which is full 10 microseconds. Okay, so the micros cancel, and you have so this comes out to be 37.5 volts. Okay, that is the primary winding voltage rating per our definition. So once that is determined, then we have a formula in the notes that relates the number of turns needed to the voltage rating frequency and the core area and the flex density that you want to allow. So that is given. Maximum flex density is 0.1 Tesla. The core area is 200 millimeters squared. So the formula that we had is N primary is V primary rating divided by 3 constants, the delta B, total change in the flex density, times the frequency F times the core area. Okay, V primary rating is already derived, is 37.5. What is delta B? So given that maximum flex density is 0.1 Tesla, so B max is 0.1 Tesla. Okay. And since we know that this is a voltage source, that is what is exciting the primary, and this can without restriction support bidirectional current, meaning the magnetizing current here is bidirectional, similar to what you see in a full bridge converter, for example. So the point is the B, the delta B is actually from negative B max to positive B max, right? So it's delta B is really a negative B max to positive B max, or delta B equals 2 times the B max allowed. Okay. And B max allowed is 0.1 Tesla, so delta B is 0.2 Tesla. That's what I'm going to enter here. Delta B is 0.2. Okay. Frequency. Okay, so you look at the waveform here, the period is 10 microseconds, which implies the frequency is 1 over 10 micro or 100 kilohertz. So that would be 100 10 to the 3 and times the AC. AC is the core area, which is given in the problem statement as 200 square millimeter. Converting that to meters squared will be 200 times 10 to the 6, 10 to the minus 6, sorry. Okay, so if you solve that, what you will have is N primary equals 9.375. Okay, so you can leave it as it is. You don't need to round it up. If you round it up, it's okay to call it as number. N primary equals 10 turns, and then the N secondary should be appropriately calculated. Okay, then N secondary, given the turns ratio N primary to N secondary is 2:1, or N secondary is 1/2 of N primary. So N secondary, N primary over 2. So from known N primary, N secondary comes out to be 4.69. So if we had approximated n primary to be 10, then n secondary can be 5. Okay, that is the main part of this part C. There is another question asked: what effect does the magnitude of IL have on the number of turns that we just calculated? So we know that these two are totally independent requirements. The current determines the area of copper needed, wire gauge, and so on, but it has no influence on the number of turns. So specifically, if you look at the equation for n primary, there is no current term or current dependent term. Therefore, I would just write IL magnitude has no effect on n primary, on number of turns, both on primary and secondary. So that's the complete answer for part C.